All right, tonight we're going to be looking at kind of an overview of how the FRC robots work in general, how we kind of divide them up, how we can look at them and see the different sections and different mechanisms, and how they all get built to play the different games that they're built for each year. Um, all of the robots are built for a specific season. So as we look, like if you've been in our lab, you've seen all of our different robots or a bunch of different robots from the previous years. We have photos up from the ones that don't exist anymore, and they all look pretty different because they're all built to specific rules. And those rules change each year, and the games that they're built for are all really different. They have different game pieces, different tasks they have to do, but even the rules themselves, so like the size restrictions, height restrictions, all of those change. So we do have to meet those specific rules each time. So as we're going through the design process, each year the robot changes a little bit as we understand the rules and what we have to build it to meet. So there's normally a max starting size. So that lately in the recent years it's been a frame perimeter. So if you like wrap a string all the way around where the bumpers go on the robot, the like bottom frame area, you get the perimeter, and that has to be under a certain length. Recently it's been 120 inches. That number could change, so we could in theory have bigger robots or smaller robots. There's normally a maximum height that you're allowed to start at, and then a maximum weight as well. So we actually weigh the robots at the event. It's part of the inspection process, so we know that we're not too heavy. So if the robot weighs 125 pounds without its bumpers and without its battery, then the robot's too heavy and we have to figure out how to cut weight. In recent years, we've been pretty good about being underweight. We try to build smaller robots, so we don't try to build to the very max size. That helps us be a little bit underweight. And then just throughout the whole build process, we're conscious of how much weight we're adding, trying to make parts a little bit lighter. And we'll normally know mid-season if we're approaching the weight limit, and then we'll start figuring out how to cut by like week 4 or 5 so that we're not overweight at the event. We haven't walked into an event overweight in a while. During the actual match, there's normally some sort of expansion limit. So there's rules about how far you can extend your robot. So you can't build a robot that just like blocks half the field in most games. I don't think in FRC you've almost ever been able to do that, not in a very long time. So normally it's like 10 inches or 16 inches or some amount of room that you're allowed to push mechanisms outside of your frame to be able to grab objects or do things. But you do have to be worried anything that's outside your bumpers might get hit, or you might run into other robots. And there's a lot of rules around those interactions and how that works. The rulebook is very specific on what we're allowed to do for the control system, what type of motors we can use, the actual computer that's running on it that controls the main motors and all the motor controllers. All of that's really specific in how we have to do things. There's a lot of things we have to do to make sure everything's legal. It's not super complicated if you have systems in place to do well, but there's a lot of ways you could do it wrong. We have a lot of systems set up and we buy the right stuff, so it's easier for us to just get it all right now. But if you come in and you've never done it before, if you're starting on a brand new team, there's a lot there to figure out. And there's a lot of safety rules as well, so there's things we can't do that are just dangerous for us to even be around, so we wouldn't want them on the robot, but also for the field or for the volunteers. So you don't want like uncovered lead. You don't want things that are going to cause damage to the carpet that we drive on, leave a big mess, so anything that can spill, any sort of like liquids, anything like that can't be on the robot. And again, they're really heavily based on whatever season they're designed for. And so as you gain more experience and you start looking at robots a lot more and you watch videos and reveal videos and things, I've sent some in some of the emails, you'll start seeing, you'll be able to kind of pick out which game a robot is for even without seeing it play the game. You can just watch a little video and be like, oh, or you can see a picture and be like, oh, that robot was clearly designed to launch frisbees, so that was from 2013, and things like that. And you'll learn that a little bit more if you start looking at robots a lot. Okay, so some basic kind of things that we'll go over first that'll make the rest of it easier. Most of the robot is powered by a couple different systems. The majority of the energy that we're able to use on the robot during a match comes from the robot's battery, and we're converting that into motion and energy using motors. So there's a variety of different types of motors we can use on the robot. These are the ones that we've used on the robot recently, which are the Falcon 500s, the ones on the left. They're basically more efficient, so they generate less heat than some of the old motors that we used to have. And they're very convenient in how they're packaged, and some other reasons, but largely you can get by if you're using the Neos next to it, the ones in the middle. Those are brushless motors as well. They're pretty much just as efficient. So either one of these are the types of motors that most teams are using now to accomplish like a lot of their bigger tasks of the driving around, lifting the robot, anything that needs to take a lot of energy. They're probably using one of these two types of motors now. And then there's a whole bunch of motors we're still allowed to use, and they kind of used to be really common in the past. We don't use them as much now just because these are newer technology and better. So for the last 3 years, since like 2020, we've pretty much been using these motors only, and it's been working out well for us. The electrical system is the entire way that the robot gets controlled. So we'll have another presentation on how all of this works, but the main idea is we have this gray box here is called the Robo Rio, and this is the main controller, so it's like the computer for the robot. This is what we're actually programming. When we say we program the robot, we have software that's running on this device here. It's communicating with the driver station, which is a laptop that has like the Xbox controllers plugged into it, so that when we move them and we drive the robot around, it's getting that information, allows us to move the motors, drive the robot around, and the entire electronics distributes the power from the battery to all of the motors, to any of the other electrical devices, sensors, anything that's on the robot that needs power. All of that happens in the electronic system. Ours normally isn't going to look specifically like this. We normally don't lay it out on a nice flat board anymore. It's moving. It gets mounted wherever it kind of can fit. Some of it gets mounted on what's called the belly pan, kind of on the bottom. We'll see that in just a second. But a lot of times things get mounted up around in different places, or there's stuff that has to run through it depending on how the robot gets built. So it's not like it's just all laid out exactly like it is on this diagram, but all of the wires are connected in the same way, and that's kind of what this is showing. Pneumatics is the other way that we can convert battery energy into motion, kinetic energy. So we do that by having compressed air. So something like this compressor here in the left under this black air tank. It is basically just a motor that is taking there and compressing the air around it into compressed air that then we can push into the ends of our pneumatic cylinders, and we can move them either forward or backwards, like this animation is showing. And so this is a really easy and convenient way to get linear motion. So if we want something to spin, we'll use a motor, but if we just need to have something in two positions, like if we need something open or close, or in or out, pneumatics are really convenient and easy to do that and have the control of that really nicely. So we do that a lot for our intake deployment, where we're trying to put something outside of the frame to like suck in a ball. We'll talk about intakes in here in a second. And so pneumatics work really well for that. So that's one of the ways that we can move things in and out. And another way that we can just power some part of our mechanism if we need some flap to open, or sometimes if we just need a simple little brake or something really tiny where you wouldn't want to use a whole motor to do it. You can use a tiny pneumatic and it can just push out maybe even just an inch, where it just moves out just a little bit. And those can work really well. Okay, so we've called things mechanisms a lot. What do we actually mean when we say a mechanism? Mechanisms, and sometimes called subsystems, are just a way for us to divide up the entirety of the robot into like their individual working tasks, basically. So each kind of mechanism gets designed to perform some kind of function on the robot. It's also how we split it up amongst the people or groups of people who are designing those different parts of the robot. So we don't have a single person designing the whole robot. We'll split it up into about 5 different mechanisms, and we'll have anywhere from 1 to 2 people leading each of those mechanisms groups as we go through the design process of going from deciding what the mechanisms are to the finished product, and like all the maintenance and everything too throughout the whole season, iterating, upgrading it, all of that. So depending on the game and how you want to design it, each robot is going to have a different mechanism or have a different set of mechanisms on it. We're going to go kind of over an example of a lot of the mechanisms categories. These are kind of broad, but most things that are on an FRC robot can fit into one of the categories we're going to go over tonight. Okay, so the first mechanism, and nearly every FRC robot has one of these, is called the drivetrain. And so this is the mechanism that allows the robot to move around the field. I say most because there have been a few games, mostly 2013 and 2015, where a few teams, a very small subset, decided that they didn't want their robot to drive. That's rarely a good idea. It did happen. There were a couple teams who did it. Most of the time, and every robot will build unless there is some very good reason, or like the game doesn't allow drivetrains or something. Like they could do that. They probably won't. We will almost certainly have a drivetrain on every one of our robots, but they do exist. The drivetrain normally includes the robot frame, so like the main structure that holds like the base of the robot together, the drive motors and drive wheels, any of the gearing or motion transfer. So like a lot of times we'll have chain or sprockets or gears or anything like that to go from the motors to the wheels. There's a term called the kit drivetrain. So if you're any brand new team to FRC is required as part of their kit to receive something that looks like this drivetrain over here on the left. This is called the AM14U. It's a drivetrain designed by Andy Mark, one of the FRC vendors. So they sell parts that are used in the robotics competition. And so this is basically the sort of standard base drivetrain for new teams and teams who don't necessarily want to design their own drivetrain. This is probably the drivetrain that the majority of FRC teams should use. I don't actually know if the majority of FRC teams do use it, but it is very well done. It's functional. It can be put together very quickly. This is the drivetrain that is used by 8515 and the EveryBot concept. So our Photon team will almost certainly be running this drivetrain as their competition robot. This is what they did this past year, and every of the new student robots that we built in the past have all been based on this. Getting experience using this is really important because there's a lot of teams who do, so we can learn how to help maintain it and fix it, because a lot of our alliance partners and things may have questions about it at events or teams that we're helping. So getting experience with this drivetrain is really important because it's just used a lot. It also is a really simple drivetrain to kind of understand the concept of, where like the 3847 drivetrain is a little bit more complicated, which we're going to go into in a second. And then we have a couple photos here from some of the past drivetrains that we've used for 3847. So this middle drivetrain is our 2017 drivetrain, and the one on the right is our 2020 drivetrain. So they can all look a little bit different. They can have different wheels. So our 2021s had pneumatic tires. These had Omni wheels, which have little rollers that allow it to like that wheel to slide side to side. There's all sorts of things you can do in a drivetrain. There are a host of different drivetrain types that we kind of categorize them all into. At this point in FRC and like the development that we've been going through over the years, the two that are on the screen right now are probably going to be the dominant and vast majority of drivetrain options that teams are going to actually choose from. Are either the one on the left, which is tanks or skid steer, depending on how you want to call it. And this is one of the simple drivetrains. If you've ever built like a Lego robot or a Vex robot or any of those, or FLL, FTC, anything like that, most of those robots use this type of drivetrain, where you just have a left set of wheels and a right set of wheels, and you have motors that power each of them. And if you power them both forward, you go forward. If you power them both backwards, you go backwards. But then if you power the right group forward and the left group backwards, the whole robot spins to the left. And if you do it the opposite, the robot spins to the right. And so this was the type of drivetrain we used in basically every competition before we switched to Swerve, which is on the right, in 2021. So all of our 2012 to 2020 robots were all tank and skid steer robots. And this is what the kit drivetrain is as well. So this is what the drivetrain type for 8515 is. You may hear the term West Coast drive. It's probably not as popular, or it doesn't come up as much anymore. But West Coast Drive is just a type of tank drive, and it's just kind of dependent on how it's built. And a lot of people have different definitions of what it actually means now, but it doesn't really matter. It's just kind of some type of tanker skid steer drivetrain. Swerve is probably the most advanced drivetrain, or a version of the most advanced drivetrains. And we've talked a little bit about it in our presentation last week when we talked about our 2022 robot. But Swerve basically is set up to where you have two motors on each of these corner modules. One of them, in this case, this motor here on the left, is powering the drive. So there's like this set of gears that it goes through, and all of these rotate, and it allows this wheel to spin. So this motor actually spins this wheel. We'll talk more specifically about how Swerve works at a future date. And then this motor is steering this wheel. So this wheel's able to like rotate, kind of like a shopping cart caster, or like a wheel on like a swivel chair or any of those, like an office chair. So they're able to rotate and be powered forward. And so it allows for that full omnidirectional motion, so our robot can drive sideways, forward, backwards, spin while driving, which the tank robot can't do, or the tank steer robot can't do. It has to kind of do arcs or spin in place and then drive forward to get to wherever it needs to go. Okay, there are a couple other types of drivetrains that exist, and we might see them, so I'm going to talk about them here. We will almost certainly never build them for competition because they have a lot of drawbacks at the FRC scale. They work actually pretty well at some of the smaller scale robots, so if you're doing like an FTC team or a VEX team, these have a lot more benefits. They don't really work well at the scale and weight of the FRC robots on the carpeted playing field that we have, and just kind of the setup with motors and power and everything that we have in FRC. These don't work as well anymore, or pretty much ever. One of them is called Mechanism. And so both of these types of drivetrains require wheels that have these special rollers on them. The wheels are just slightly different. So a Mechanism wheel has 45-degree rollers, so they're off at these like angles. And they're set up in such a way that you have one on each of the four corners, and they're kind of set up similarly to a tank drive, where you have a left and a right set of wheels, but because their rollers are pointed in different directions, and we can go into this a little bit more at some point if anyone's curious, when you run one set like into each other, so you literally have this front wheel running backwards and this back wheel running forwards, and then the opposite on the other side, the robot's able to drive sideways. And so you can get, it's kind of common to think, oh, we could just do this instead of Swerve and they can still do the same things. And that's not really true with the way that the FRC robots work. You end up just not having the same amount of power. You're wasting a lot of energy in the way that it slides sideways and things. They can be pushed a lot easier. So they just don't work the same as actually doing the full Swerve robot implementation, or the full Swerve drivetrain implementation. You will still see teams do them sometimes. There have been teams who have done them successfully. 1986 Titanium, there's a team that did it in 2017 and were like world finalists. So like it is possible, but it's not nearly as easy, or like there's a lot more teams who do worse with Mechanism than with doing Swerve. A similar option is called OmniDrive, X-Drive, or Kiwi. Basically, it has Omni wheels that are, instead of having just like these rollers at 45 degrees, you have the whole wheel at 45 degrees. And then it works very similarly to Mechanism in the same, like it's actually, the software is all exactly the same. But it has a lot of the same drawbacks, limited traction, pushing power. Swerve is just better. A couple other things that people try to do, and again have varying levels of success with. H-Drive tries to get some of the advantages of tank while still being able to like drive sideways. So you end up having just like a tank drive on the left and right, and then you put another Omni wheel in the middle. So all 5 of these wheels are Omni wheels, so they'll like slide sideways. You can see like these rollers would be able to slide sideways. And so if you just powered this middle wheel, the robot's able to go back and forth. And it kind of works. And there have been teams who are successful with this as well. But in general, Swerve is just going to have a lot more advantages over anything like this. And then there are teams who try to get some of the best of both worlds, and you try to do combination or articulating drivetrains where you can like switch from mechanism to tank. Again, they can work. Teams have done them. Teams have had success with them. Swerve or just standard tank is normally going to be better for the vast majority of teams. But I wanted to go through them so when you see other robots with them, you kind of have some idea what they're doing. You'll probably see them a lot less. Again, the vast majority of teams now are going to be running one of these two as they've just been shown to be better in competition than the others at this point. Okay. You've seen bumpers. I don't know if everyone understands exactly what they are or what's actually happening. They're really, really simple, but they can also be a little bit difficult to create and make well. So the bumpers on each robot are how we tell alliances. So we have a red and a blue set. Each robot has to be able to display red and blue. Some teams do a weird thing where they have like reversible bumpers. We've never been a fan of that. We always just build two separate sets. You can kind of think of these basically like football pads for robots. The construction is rather simple. It's literally just a piece of plywood and then foam pool noodles wrapped around it and then fabric wrapped around that. So there's nothing super complicated about actually building them. How they actually mount to the robot and things gets a little bit complicated, or maybe we just make it complicated. And this is also where we put the team number so it's easy to identify which robot is which on the field as well, because if you can see the team number, you know which team it is. Okay, so going into some more of the mechanisms that are going to be game specific, we have things like a floor intake. Most games are going to need to be able to pick up whatever the game piece is off of the ground. This isn't always true. There are some games where it's better or possible to run without one. Not every game piece makes sense to be picked up off the floor. Sometimes the games are built to where you can get them from a different thing. We'll talk about the human load in a second. But most of the time we're going to have some sort of intake that's able to spin a game piece and pull it up over the bumper or through maybe a gap in the bumper. You're allowed to have gaps in the bumpers in certain years most of the time. And bring it into the robot so then it can get moved in some way into a scoring position. So on the left here we have our 2018 intake, and this was used to pick up cubes. So these wheels would grab the side of the cube and spin it into place and like get it flat to the back and hold it well, so then we could lift it up and put it in the goals that existed that year. These two pictures here are our 2020 intake and a prototype version of it. And so this is rather simple. It just has rollers that spin and suck the ball up off the floor and put it into the robot. And this is pretty much what our 2022 robot does. Most of the ball games, you have something similar to this, where you have some sort of spinning roller that just spins it up over the bumper and into the robot. We had a few other, there's been other games where we've had different versions of these rollers. You might have wheels that do it. Something to grab the game piece that's sitting on the floor and bring it up into the robot is all it is. But it ends up being one of the more important parts of the design, because in most games, if you can't reliably and quickly get the game piece into the robot, you're going to have a very hard time actually scoring a lot of points very quickly, because that's one of the tasks that has to be done super easily, or it has to be done a lot to be able to actually score points. So you need to make it super easy for the driver, who might be 50 feet away from the robot, to be able to just drive into the game piece, hit it, have it being brought up into the robot, and then for them to be able to go score it really quickly. The other type of intake is a human feeder intake. So this is where its entire purpose is to get the game piece from some sort of slot or ramp or something else on the field where the human can deposit the game piece. So the pictures that we have here are from the 2017 game, and they had these ramps that the human could drop these gear game pieces down. And there was a slot here. It's kind of hard to see because it's all polycarb, so it was all clear. But there's this ramp here that we would deploy out the back of the robot. It would basically flip down, and the gear would fall into it, and it would get placed right into this little cage. and then that was how you had to score it that year. There were like these springs that went through the gear, and you would leave it there, and that was how you would score points. So that whole intake was designed to get from the human player station, and then at the front of the robot up here, actually where the spectrum is, that was our floor intake for gears, so we could flip that down and we could roll a gear in from the floor as well. So we had two different intakes for the same type of game piece. We had a human feeder intake on the back and a floor intake on the front. And so depending on how we were scoring at the time, you could use either one. Okay. The last thing on human player intakes. A lot of games, it doesn't make sense to have a human feeder intake because it's just not going to be faster. So like the 2022 game, we could build something to have gotten from the human player station. There's like a ramp there to roll the balls back in. And you could have built something to take a ball from that. But there weren't any real necessity to or reason to, since the human players didn't start with balls. There weren't a ton of balls there to get. It was much better just to focus on the floor intaking and have the human player just throw the game piece out onto the floor every time. And that may work in a lot of games. So it kind of depends on what the game situation is, how it all functions, depends on which type of intake you want for that game. Hopper and indexer. So in games where you're allowed to hold multiple game pieces, you normally have to have some place to store them and organize them so that you can score them quickly. In 2020, we were allowed to hold 5 balls at a time, and so he had this like V-belt hopper where we had these black belts that could spin and bring the ball up into the ball tower. So we would store them by putting 3 balls in the tower and then 2 balls in these like V-belts right here. And then those would basically be in our organized system ready to fire, so that when we were ready to actually launch the balls, we could do that very quickly and organized and get them out of the robot into the goal very quickly. So there's a whole variety of ways to do this. A lot of them depend on the game piece. So sometimes you're just like stacking them and storing them in a stack and somehow taking them off the stack. That's kind of what most teams did for like the Frisbee game. You just have a stack of Frisbees. Sometimes you have a stack of totes. Sometimes the game piece you're only allowed to hold one at a time, or it's a penalty. In those games, you normally don't have any sort of hopper or indexer. You normally just have some place where you're storing it, like the 2018 where we just had the claw. That was where the game piece was stored. And so that's normally fine. 2019 was similar. We just had a single like storage box for the one game piece we were allowed to hold at each time. But if it's a game where it's multiple, that ends up being a pretty good challenge, because sometimes like this specific game, these balls really like to jam a lot, so they would like squish together, and if you didn't have a pretty good design, they would not want to go where you told them. So instead of like going up to the launcher wheel, they might end up getting shoved into like some corner over here or something. Like we had that happen even. Like we had a ball stuck in weird spots on the robot because these balls were just so grippy and would like to just compress into weird areas. Okay. Wheeled launchers are the next type of mechanism. So this is one of the simpler ways to launch game objects. Like we said earlier, motors are the most efficient way for us to get energy out of the battery. And so if we can just spin something really fast and complete the game task, that's why most of the intakes are just spinning a roller. Most of the launchers that we've built in the past are just spinning a wheel and having the ball go through it. These work very similar to like a baseball pitching machine you might have seen, or a football launching machine like a jug machine. They all have like roughly the same concept. You just have a very fast spinning wheel. The game object goes through it, or whatever the launching thing that you're trying to launch goes through it, and gets thrown into, hopefully directed at the goal. So this was the 2020 goal. It had this octagon or hexagon that we were trying to throw it through, sorry. And so we've had a variety of different wheels that we've been able to use in the past, but they all have roughly the same concept. It's just spinning a wheel really fast. And then there's a lot of detail in how you make sure that the ball actually gets presented to that wheel and like pushed into it consistently. So it might work where you can throw a ball out really fast, but part of it is, can you do it really reliably and get kind of the same, hit the same target over and over again, so you can actually make all 5 of those balls. You see in that video, if we weren't consistent, if we didn't have the whole system tuned properly, It might be that we shot 5 balls and only 3 went in or something, and that's not what we want. We want to make sure every time a ball leaves the robot, it's going in ideally in the same place. This was pretty early, so this was still our like prototype robot, and so the path gets a little bit weird. So that first ball goes a little high, and then the next 4 are all about the same. We tried to work on that in the competition robot to where they were all trying to follow that like same line out, and we could be very consistent with all of our balls, and that's normally what you want in a game. Wheeled launchers aren't the only way to throw things. Catapults also work. So in 2014, that's what this is the robot for that game. We had these very large balls as our game objects. These are about 24 inches in diameter, I believe. I think that's right. And so it was tricky to shoot them with a wheeled launcher. Actually, the team that ended up winning the world championship did that. They actually just used a wheeled launcher, and more teams probably should have. But I don't think a lot of teams realized, we didn't realize that we could. And so instead, teams built Catapult. So all 3 of the robots that are launching balls here are all using a Catapult. This was ours in 2014. So the intake kind of deploys, and then we have that Catapult flick up and launch the ball into the goal. This other robot does the same thing. You can see it just has a pivot here, and there's basically, they just have elastic tubing that they pull back. So they just winch back the elastic tubing with a motor, and they release it and launch the ball. I believe at this point, this is at Lone Star, so we were using pneumatics. So we used a pneumatic catapult here to fire the ball. And so in certain games, especially if you only need to launch a single game piece at a time, catapults can be very consistent and can package well, and so they work rather easily for games like this. The 2014 game saw a lot of catapults, and the 2016 game saw a lot. There were a few even in the 2022 game, this last game that we saw. There were a few teams who even managed to do like double catapults. Since you're allowed to hold 2 balls at a time, they built 2 catapults and would just fire both balls, 1 from each catapult. So if you do have a limited number of game pieces, catapults do work and can be effective. Okay, so those are normally the 2 ways to launch game objects. There's probably some other obscure ones, but most of the time it's going to be a wheeled launcher or a catapult. Elevators are probably the next most common mechanism on FRC robots. We've had a lot of games where we've launched game pieces. Starting in 2006, there were at least a half dozen games where we've launched balls or frisbees. We've also had a lot of games where we've had to score game object at various heights. So this is the 2019 game where we have an example here. So you had to put these hatch panels, which were these discs with Velcro on them, and you had to put them at one of 3 different heights. And then you also had cargo, these orange balls that had to go in behind them at one of 3 different heights as well. So most teams built an elevator so we could move up and down whatever our intake was, however we were storing the game piece, or the game pieces in this case, and get them to the right height so we can score them. This is going to be one of our fall projects. We've already started looking at some of the design work, but we're basically going to build a full elevator because we haven't built one in a few years. The last one was 2019. And so there's a lot of different, our technology, our ability to manufacture things, how we build stuff, a lot of that has changed. So we want to make sure we have some idea how to build an elevator, because it's possible that we'll get an elevator again in the next few years and need to build one, or some game that makes sense to have an elevator again. So you'll see a lot of these on past robots. There's a lot of different elevator designs and a lot of different ways for teams to do this, but they're all roughly the same. They have this same kind of structure of things moving up and down, where this outer frame is like stationary, and then there's this inner one and another staged right in the inside, which is panel right here, what we call the carriage, was what held the rest of the all the intakes and things to it, and that was what slid up and down. There's a lot of different ways to power it. You can have like chain and sprockets move it up and down. You could have a rope. There's all sorts of different ways to actually move it up and down as well. The other way to lift game objects up into the air is with an arm. We've only built one robot that had an arm. We shouldn't have built an arm this year. This was probably a mistake. We probably should have built an elevator in 2018. This is the 2018 game. These are the cubes that it was designed to pick up. And the robot did work well. We won an event with this robot, so it was okay. But we definitely would have been better off had we built an actual elevator. But so you can build an arm with the pivot at different points. So in this robot, the pivot kind of pivots in the middle, and then it actually has an extension, so it could actually extend this whole thing up another like 2 feet, so it gets closer to these taller goals that exist in the back that it had to put it on. You could also have an arm that pivots like all the way at the back if you wanted a lot of extend, or if you wanted a lot of reach for some reason. Arms work if you're trying to extend really far over something instead of just up. An arm might make sense. But again, we probably won't build a big arm anytime in the future. Most games that we would need will probably end up building an elevator instead if we have to reach up high. The technology is a lot easier, and they're normally more robust. They have less chance of like falling over. The game object stays like the same distance away, so the driver doesn't have to adjust as much. There's a lot of advantages to elevators over arms in most games now. If you make a small arm, we basically call those wrists. So arms are kind of this big thing that's going to move, kind of like the main motion of everything, and it's going to do a lot to get you up to your scoring task. Wrists are just there normally to deploy something in and out kind of quickly, and a lot of times they're like a single small pivot. So this is how we deploy our intake. So we had pneumatic cylinders that pushed up and down so that we could drop the intake in and out. We did the same thing in 2022. We had an intake that came in and out with pneumatics. You could also do it with a motor. So our 2017 floor intake for the gears, you can kind of see it, there's a person in the way in this clip, but it folds down and goes down to the floor to grab the gear. And then there is a wheeled intake, so there's like a roller that sucks the gear in. That yellow thing is the gear. And then it places it on the scoring object, which I think the clip ends before it actually scores it. But so that's another little wrist that was motor powered, and it works pretty well as well. So there's different ways to move the wrist in and out: pneumatics, motors, gears, chains, sprocket. There's all sorts of ways, and we'll get into a lot of those as we move on. But just get an idea of what they are and how they work. So this ends up being a lot of times that you'll have some sort of wrist mounted onto an elevator so that you can fold down and grab whatever the game piece is, then fold back up and then raise it up and down to go and actually score it. And that's kind of a very common way that FRC robots are built. All right, one of the last types of mechanisms is the climber. And this is going to be very common for a lot of games. The sort of the end game task, whatever it is that the robot has to do at the end of the match, in a lot of past games have been climbing of some sort. So I think all the way back in 2004, there was a game where you had to pick up and basically have the robot do a pull-up. There have been various iterations of robots doing pull-ups for a long time. Not every game has a climbing task, but just a lot do. So yeah, so you have here 2020, 2022, 2018, 2016, 2013, all had end games that were basically some type of elevator could be used to pick the robot up. 2022 added the stage where you had to go from bar to bar, which needed a little bit more mechanism to make it work. But you could definitely build some type of elevator to make it work. You can also have some type of winch and deployable hook. That's kind of what we did for 2022 when the robot deploys the hooks out and then it winches them back in. There are a few other types of climbs that can exist. The 2019 game, the robots had to get up on top of a platform. So those climbers are all a little bit different. In a few games, they've also had robots have to lift other robots. So like 2007, the end game was to basically be able to put one of your partners 12 inches into the air. So teams like built ramps and things. So those are possible. So there are various forms of type of end game and climber mechanisms that might exist on robots. And like the final type of mechanism is all things that are going to be to directly interact with a specific part of the field that gets built that year. So as we go back and you start looking through the animations from past games, or you start looking at past robots, you'll see a lot of different, there's quite a few different times in FRC where the robot had to move something or do something on the field to either get to a certain area or to score specific points. They had to actually like interact with the field. So in 2012, there were like full teeter-totter bridges that instead of doing a pull-up, you actually had to like drive up onto this bridge and then balance it. So if the bridge was flat, you got more points. So one of the field manipulation mechanisms was to be able to make sure you could push the bridge down so your robot could actually drive up onto it. 2016 is the game that probably saw this the most because you had what were called defenses. So there's kind of a photo here you can see. So all of these little areas had different things that the robots had to drive over. Some of them were kind of passive. So like right here is just the big like, it was called the rock wall, and it's just a block of steel. So it was about, I think it was only 4 inches tall and like 6 inches wide, and the robot had to be able to drive over that. The one that's being driven over in this picture was called the Cheval de Frise, but really it was just another like set of teeter-totters. So we had to tilt down these Lexan ramps and then drive over them. There was also a drawbridge that you had to move up, or you had to pull down the drawbridge, sorry. There was the portcullis that was like a fence that you had to move up to be able to drive under. So there was a couple different things that you could have your robot do to manipulate the field, and there were different little mechanisms you could build. And then in 2020, there was a control panel, or also called the color wheel, and you had to spin it to a certain place so that a sensor could see a certain color, or spin it enough times for a number of rotations, and you would get points for doing that. So there were some mechanisms that were built that were specifically designed to spin this one wheel thing that was on the field. So they could bring back something like that. There might be a game where you have to push certain buttons, or move certain things, or turn certain things, or flip a panel or something. There's all sorts of things they could give us in a game, and those would kind of all fall under the field manipulator mechanism task. And a lot of those are going to be super specific to whatever that game is that year. Okay. So we are finishing up. One of the ways that you can start looking at some of these different mechanisms and how they work is through our mechanism library. So mechanisms.spectrum347.org will take you to our photo gallery. And we need to go back into some of our past years. We don't have anything for 15 and 14 right now. But for quite a few of them, you can go in and you can click through. So say for, I think 2016 is a decent one. You can go through and be like, oh, I want to look at all the intakes in 2016. And so you can click intake. Oh, this one actually doesn't have that many. Let's go back. Let's go to something a little bit more recent. Maybe 2018. So if you want to look at all the 2018 intakes, that one has a bit more. There we go. So you could go through this and you could actually just look and see how different teams built their intakes in 2018. There's a variety of them. You can do the same thing for the different years. So if you're just trying to say, oh, maybe there was some game I wanted to see how a team did something, or just get an idea. Well, there's for some reason no intakes there. That's weird. Elevators in 2019, there's various photos of them. You can see a lot of detail in how they built them. So we try to go through and make this better. If you want to help make these mechanism libraries better, we can go through and show you how to tag the photos. So we have a lot of photos. We have thousands and thousands of pictures of other robots. But to get them in our mechanism library, we have to tag them. And so if that's something you want to help with, we would definitely greatly appreciate it, where you can just go through the photos and say, oh, there's an elevator in this photo, there's a intake in this photo. It definitely doesn't have to be 100% perfect. You don't have to get it always right. It's fine if there's a few errors. But yeah, we can go back through the past and see some of these.